In this lesson, we take a brief excursion through the world of computer modeling and simulation to illustrate how these tools can support the development of hydrogen applications. In this context, we pick out three use cases, in particular simulations supporting process development, simulations of single processes, and holistic simulations that place a process in a broader context. Starting with simulations supporting process development, there are various typical use cases. First of all, computational fluid dynamics, or CFD, can be used to solve problems that involve fluid flows. For example, the flow in a pipe, or the flow across a catalytic surface, for which the interaction of the fluid with the surface is of importance for mass transfer and the chemical reaction on that surface. Second, a major challenge is the determination of unknown thermophysical property data, which are required for the application of rigorous thermodynamic models. Examples of such data are, in particular, mixture properties like densities, caloric data, dew points, or transport properties like viscosity, thermal conductivity, and diffusion coefficients. For such data estimations, specialized software tools are available, for example, those provided by the Dortmund Data Bank. A further issue is the estimation of fluid phase equilibria, in particular of mixtures lacking experimental data or at inconvenient states. For this kind of problem, molecular simulations can be used. One powerful method is the Gibbs Ensemble Monte Carlo method, which uses two simulation boxes, one for each phase of interest, and provides thermophysical property data of the boxes in equilibrium. In the example shown here, a vapor-liquid equilibrium is simulated. Last but not least, many novel processes for hydrogen applications involve chemical reaction on catalytic surfaces. To model the kinetics of such reactions, kinetic Monte Carlo simulations are the method of choice. In this example, we see the surface of a catalyst, which is empty in the beginning and is then exposed to the adsorption of two chemical species. These species are first chemisorbed on the surface, can furthermore be physisorbed on additional layers of their own species, and can finally react with the other species and leave the surface towards the surrounding bulk phase. In this way, the influence of different surface structures of the catalyst or different gas compositions can be studied and used to optimize the catalytic reaction. Once the required physical property and chemical reaction data have been determined up to a certain degree, that allows the application of rigorous simulation models, the novel hydrogen process can be depicted in a commercial simulation program for chemical and process engineering applications. Here, the process is split up into unit operations that are connected by material streams, and the simulation program solves the related material and heat balances and provides a basic layout of the process equipment. Such single process simulations can be used to design, analyze, and intensify the process by conducting case studies that vary the process conditions or the feed streams. And in this way, the process itself can be optimized. Furthermore, these simulations can support and prioritize alternative innovations and can be used to scale up new technologies into commercially available pathways. Last but not least, they can also assist in minimizing cost and risk across the asset lifecycle, from technology selection through full-scale operations. However, the optimization of a single process is only a first step. Instead, it is necessary to carry out a holistic simulation of the process in a broader context in order to quantify its impact on resource requirements and CO2 emissions. In this connection, one may want to include data-driven black box models, like artificial neural networks, that rely on experimental data and can be used to describe complex phenomena of the process that cannot be described by the rigorous models that are provided in commercial simulation software. Such black box models can then be connected with the rigorous white box models from the commercial simulation programs into an overall gray box process flowsheet. In the next step, such a combined flowsheet can be used in the course of a multi-objective optimization as a stress test for the individual process in the field of competing interests. This is illustrated by an example diagram that shows the results of a multi-objective optimization, targeting at maximizing the margin on the abscissa while minimizing the CO2 emissions on the ordinate of the diagram. As this situation means two conflicting objective functions, not a single optimum can be found, but rather a best trade-off curve can be obtained at which, at a fixed point of one objective, no better solution of the second objective can be found. This best trade-off curve is shown in orange and is called a Pareto front. In this way, such a holistic approach can help to decide how to position the process between conflicting influencing factors. Now, to summarize this lesson, modeling and simulation can be key factors in the development of novel hydrogen applications. Modeling and simulation tools support a deep understanding of processes, their optimization, and their impact on resource requirements and CO2 emissions.